Modern satellites for applications such as Earth observation, navigation and telecommunication are advancing at a rapid rate. To keep pace with their evolution, new high-performance satellite subsystems for the fast and efficient management of high volumes of data are required. HiSide has developed the next generation of integrated technologies for the high-speed processing, storage and transfer of large amounts of satellite data with the objective of remarkably improving the speed and efficiency of onboard data management and transfer to ground. The project made substantial advances in the performance of individual components of the data chain, including the development of a high-performance, high-reliability and high-availability network to interconnect the data chain elements, a modular data compression system which can process the very high instrument data rates foreseen for future Earth observation missions, a high-performance, versatile payload processing unit that can be programmed on the fly in 40 microseconds, a high-rate RF downlink transmitter, including Ka-band modulator, Ka-band solid-state amplifier, and a ground station demodulator, which combined provide high-speed data transmission from Earth observation or data relay satellites to the ground, an optical terminal system that supports high-speed data and optical downlinks, and a file protection scheme, which protects files against loss of data due to outages in optical downlinks from satellite to ground. While these individual advances represent significant improvements to current satellite payload technologies, HiSide's main innovation is the demonstration of a complete data chain architecture to handle an aggregate instrument data rate of at least 50 gigabits per second in the near term, together with a roadmap to achieve performance greater than 100 gigabits per second in the future. The Space Fiber routing switch is a core component of the HiSide onboard network, which uses the emerging high-performance and extremely versatile space fiber technology to interconnect the data chain elements, providing consistent interfaces and common configuration, control and housekeeping capabilities, as well as supporting very high data rates. Produced by Star Dundee, the Space Fiber routing switch is a 10-port multi-lane switch supporting 10 gigabits per second data rate on each port. 2 ports have 4 lanes, and 8 ports have 2 lanes, with lane rates of 6.25 gigabits per second. The Space Fiber interface and routing switch IP cores provide the basis of a highly capable space fiber network and form an essential element in many space fiber applications.
The particular routing switch we've designed is called Star Tiger. It's effectively like the heart of the spacecraft, pumping the information around the spacecraft. So you need the routing switch in the middle, and you need space fiber interfaces in each of the pieces of equipment. Instruments are becoming more and more sophisticated, able to gather more and more information about the Earth, whether it's images of the Earth, surveillance, environmental purposes, maybe radar instruments that are looking at topology of the Earth and movement of volcanoes, etc. All of these instruments generate a large amount of data. So then we have to get that information down to ground, and the downlink is a major bottleneck. So on board the spacecraft, we need to process the data, maybe compress the data. We want to encrypt it to make it secure. There may be some other processing we want to do, like cloud recognition, so that we don't send down cloudy images. We just use the bandwidth for sending images that are useful. So all of that information needs to be passed around the spacecraft, from the instruments to the onboard mass memory, to the downlink telemetry system, to the onboard compressors and onboard processors. And that's what the onboard network does. And the key element in there is the Star Tiger routing switch. We send information in packets, so these are like electronic envelopes containing information. Those packets arrive at the routing switch. We look at the address which is on the front, and using that address we determine which port we've got to send it out of to forward it to its final destination, and then it gets sent out. Now that happens very, very quickly, so it takes less than a microsecond to do that switching and forwarding of the packet. So it's very fast to handle the high data rate and give us low latency. The other thing we have is fault detection, isolation and recovery. So over each of the link, we detect if there's been an error on the link and automatically resend the information if there's been an error. Detection of the error and resending the information only takes 3 microseconds. So basically outside the link, you don't see the errors at all. And it does that all autonomously. So we set up the network with software, and once it's set up, it just runs itself without any processors having any interaction with the network.
Produced by Airbus Defence and Space, the data compression module integrates CCSDS 123.0 B2 IP cores designed by the Digital Systems and Computer Architecture Laboratory of the National and Kapodistrian University of Athens, and a cross-reference verified software implementation developed by Universitat Autònoma de Barcelona. The module provides onboard data compression functions and is capable of storing hyperspectral images at 7 gigabits per second using CCSDS 123.0 B2 based compression. Thanks to this performance, we can store more data in the satellite and transmit data with a faster speed to the Earth, meaning less time is required for connection and thus less bandwidth is utilized.
The aim is to provide a solution, a high-speed solution that can work in two modes. A bypass mode where data can be buffered and stored as is before being transferred to the other elements of the chain. And the second mode, which is more intelligent, let's say, is where the data is compressed in order to reduce the size before again being stored and forwarded to the other elements of the space fiber network.
The High Performance Data Processor, or HPDP, implements a systolic array architecture with the ability to parallelize algorithms and thus provides speeds many times faster than a single processor. Produced by ISD, the HPDP element is a printed circuit board composed of a field-programmable gate array and custom processor, enabling low power and versatile computational capabilities. The HPDP offers 40 giga-operations per second capability with 1.65 watt power consumption. This low-power, reconfigurable, high-performance node is new for the European landscape and will enable more onboard computations in European satellites.
Within the overall network, we have several sources of data. So we have a camera and an instrument simulator. And so all of that data has been generated at high data rates, and it needs to be stored somewhere before it's transferred down to ground. So that's stored in the mass memory. So if you're on a spacecraft and you don't necessarily have constant contact with ground, then data essentially needs to be buffered for a certain amount of time before it's transferred to ground during a window of opportunity. The instruments generate data that conforms to a specific format called CCSDS space packets. And those are encapsulated within a further packet format that we use within HiSide. So what the mass memory does is it looks at the information within those headers and filters traffic from different application sources into different files so that you can maintain separation of data between different sources. When you want to transmit that data back to one of the downlinks to be transmitted to ground, the control computer sends a command to the mass memory to initiate that operation.
The RF downlink provides transmission of Earth observation data from space to ground. The downlink is composed of a 1G baud 5 gigabits per second Ka-band modulator provided by TSAT, a 2-watt Ka-band solid-state power amplifier provided by Earthsia, and a ground station demodulator provided by Kongsberg Defence and Aerospace. Together, these components make up a verified end-to-end RF downlink solution. The RF downlink is capable of transmitting at a symbol rate of up to 1 gigasymbol per second, corresponding to a user data rate of up to 5 gigabits per second per carrier, which is twice the capability of today's systems. The RF downlink demonstrator developed within HiSide is considered the first step towards a future space product.
What we have developed is a demonstrator for an RF downlink. It is needed to transmit data from satellites to ground. The RF downlink consists mainly of 3 elements. It is a modulator, which is modulating data onto a radio frequency carrier. It's also encoding the data. Then we have the amplifier after that modulator, which is also developed for this project. And then normally we have an antenna, which then focuses the signal towards the Earth. So the RF downlink is located on the satellite, of course, and it has a data interface, a high-speed data interface to the to the space fiber router, which serves for switching data, for example, from the mass memory to the modulator or from instruments to the modulator. So that means that the RF downlink has two interfaces in the data chain. One is to the router on the satellite and the other is the RF signal down to Earth.
Developed by the German Space Agency, DLR, in cooperation with TSAT, the HiSight optical terminal supports data rates of up to 8 gigabits per second, with optical downlink rates of 10 gigabits per second. The optical downlink will provide a viable alternative to overburdened radio frequency technology and addresses increasing demand for free space optical technology in 3G and 4G network architectures.
So we have been developing in the last few years a complete program for optical communication systems over satellites. Here the idea is to provide a system that is capable to download data to Earth at very high data rates, thus providing a very high throughput for the users. In this particular project for HiSight, the aim is to then be able to use the available bandwidth that is provided by the space fiber technologies, so that the user can actually get the data out to ground and use it effectively. The optical downlink is needed within the HiSight project and as part of a system featuring space fiber technologies, because we need a way to exploit the high data rates and processing power that this allows for future Earth observation missions. So it makes sense that we are increasing the processing power on board, but then you need a way to also take this down to Earth. And the way to achieve this is by optical communication terminals. We are a very interdisciplinary team in which you also have colleagues that are working on the development of the mechanical parts, the optical parts, the electronic parts, and I'm in charge of the firmware development for the system, operation, control, and everything that is related to the required software.
In June 2022, HiSight demonstrated the products developed as part of an integrated data chain at Star House in Dundee, Scotland. A series of typical data management scenarios were implemented, and we successfully demonstrated the capacity of the integrated chain to store and playback images from a space fiber camera at 9 gigabits per second, compress and store hyperspectral images via the data compressor at 7 gigabits per second on a CCSTS 123.0 B2 based compression, encrypt and store files via the high-performance data processor at 70 megabits per second, transmit and playback images via the RF downlink at 5 gigabits per second per channel, transmit data via the optical downlink at 9 gigabits per second, and demonstrate packet error burst correction of up to 25% using the file protection scheme. This demonstration proved the capacity of the HiSight HSDC architecture to process, store and transmit data from instrument to ground at data rates of up to 10 gigabits per second, which was the original target of the HiSight project.
The HiSight project had partners that were selected for their expertise in certain areas, and they really have all delivered well on the project, and seeing the whole thing integrated is fantastic. So all of that technology will move forward. All of that is just what's needed for future space missions, particularly Earth observation missions, but also potentially telecoms missions as well.
The technology demonstrated in HiSight technology is of immense social and economic value, and will enable future Earth observation satellites to be equipped with instruments that provide higher resolution and more detailed data than was previously possible, improving the quality of data available for these critical applications and future-proofing Europe's fleet of Earth observation satellites.